In all times, people have formed an image of how the world works on a large and small scale. In earlier centuries and millennia, knowledge about nature was called natural philosophy. This is how modern science developed. Today, physics in particular would like to give an answer to the question of what holds the world together at its core. To do this, we need to take a look at the geometry. Geometry has been a subject since ancient times. We all know the Pythagorean theorem from school. The word geometry actually means earth surveying. At that time, people imagined that the earth was flat. So lines and areas have been represented on straight planes. This is what we now call Euclidean geometry. The ancient philosopher Euclid is called the father of geometry. In modern vector representation, it is the basis for the mathematical description of geometric structures in almost all sciences. If we stick to the survey of the Earth, today we have to do it on a spherical surface. We then see that a line connection is not straight, although we always walk straight ahead on the globe. Triangles drawn on a sphere are also curved. This type of geometry is called spherical geometry. The theory of curved spaces was developed in detail by the mathematician Bernhard Riemann.
Now let's turn to physics. Modern physics has developed since the Renaissance period. Since then, experiments have been carried out in order to find and describe the laws of nature. Until Einstein's time, the foundations of physics were determined by the achievements of Isaac Newton. He described the law of gravitation and thus found a universal law according to which celestial bodies attract each other according to the inverse square of the distance. A second law concerns the course of movements over time. The acceleration experienced by a body is proportional to the force acting on it. In short, force equals mass times acceleration. This force can also be of electromagnetic origin. The speed is calculated from the acceleration, which is why we speak of dynamics. This is also a universal law. The theory of electricity, also known as electrodynamics, was developed in the 19th century. This was brought into a uniform mathematical form by James Clerk Maxwell. They are called Maxwell's equations. It was found that light is electromagnetic radiation. However, this led to difficulties with Newton's equations of motion. Because Maxwell's work showed that the speed of light is the same in all frames of reference as long as these frames are not accelerated against each other. Albert Einstein solved this problem a few years later. He developed a theory that was then called the special theory of relativity. This means that lengths and durations are perceived differently by different observers. They depend on the state of movement of the observers among themselves. This is not known from everyday life and is therefore not clear. However, it represents progress in the description of nature, because, according to this principle, all mathematical equations of the description of nature assume a form that is independent of the state of movement of the observer. One can therefore say that it is an objective description method. After Einstein had successfully taken this step, he wanted to extend his methodology to systems that are accelerated against each other. This is the more general case. He worked on this methodology for 10 years and then called it general relativity. This can be explained as follows. In space, the planets are attracted by the central star and therefore follow elliptical orbits. The force responsible is called gravity and causes an accelerated movement that is directed towards the central star. Einstein was therefore able to include gravitation in his general theory of relativity, which deals with accelerated movements. However, He could not use Newton's equations for this, since these do not meet the requirement of being independent of the state of motion of the observer. Instead, he chose a new geometric approach, namely Riemannian geometry. Einstein's general theory of relativity is thus based on a curvature of space. On the basis of Riemann's geometry, Einstein defined an equation of motion, called Einstein's field equation. Its solution then results in the curvature of space. This approach was completely new in physics. One speaks of a paradigm shift from Euclidean to Riemannian geometry.
However, this paradigm shift only affected the mechanical sector of physics, like gravitation. It was not possible to describe Maxwell's equations of electrodynamics in this way, they only satisfy the special theory of relativity. The same applies to quantum mechanics, which was developed shortly after Einstein's discoveries. It therefore remained a pipe dream to have unified physics, as had been the case before Einstein and Maxwell. In the meantime, however, there has been a further development in mathematics in the field of Riemannian geometry. In the 1920s, the French mathematician Élie Cartan found out that in addition to the curvature of space, torsion also plays a role. Both are even linked to each other. A curvature of space always causes a torsion and vice versa. You can even study this on the human body. The concept of torsion was therefore already known at the beginning of the 20th century, but it was believed that it played no role in Einstein's general theory of relativity. Cartan pointed out to Einstein that torsion can also be used to formulate Maxwell's equations within the framework of general relativity. However, Einstein did not understand Cartan's mathematics, and so this connection was ignored. It wasn't until around the year 2000 that the Welsh physicist Myron Evans finally took up this idea again. He succeeded in showing that all areas of physics can really be unified in this way. That was the beginning of another paradigm shift. Myron Evans was the gifted son of a miner's family in Wales, Great Britain. He studied physics and worked in the field of spectroscopy, first in Wales and later at several universities in the USA. He has won several research awards for his outstanding results. However, his fellow professors envied his success, as he was able to produce as many scientific papers with new content in a month as his colleagues could not do in a whole year. This stressful situation eventually led to a nervous breakdown for Evans, which is why he returned to his hometown in Wales in 2000. From there he developed the Einstein-Cartan-Evans theory, or ECE theory for short, from 2003 onwards. As early as the 1990s, Myron Evans and colleagues founded the Alpha Institute for Advanced Study, AIAS, which is an informal association of scientists from various disciplines. He headed this until his death in 2019. Horst Eckhardt then took over the continuation of the scientific work. Between 2003 and today, more than 450 specialist articles have been published in which all subareas of ECE theory have been developed. In addition to Myron Evans, Douglas Lindstrom and Horst Eckhardt were mainly involved. Evans realized that he could use Cartan geometry, that is extended Riemann geometry, to formulate electrodynamics. Einstein failed to do this. Evans thus made electrodynamics compatible with general relativity, without even fundamentally changing the form of the equations. Mechanics, gravitation and fluid mechanics were then formulated and unified by the Cartan geometry according to the same principle. Quantum mechanics, as well as the weak and strong nuclear forces, were also managed to be included accordingly, so that all areas of physics are unified with it, and ECE theory can be regarded as a theory of everything.
ECE theory describes the universe in essentially the same way, from the macroscopic world of supergalactic clusters to the smallest microscopic world of quarks. Quarks are regions of spinning spacetime. Galaxies are also regions of spinning spacetime, and this gives an appealing view of the whole universe.
Now let's take a closer look at the Cartan geometry before we get to its physical interpretation. In Cartan geometry, the four-dimensional space is used, consisting of three spatial and one-time coordinates, as used by Einstein. However, one distinguishes between the basic vector space, the manifold, and a tangent space, which is defined at each point of the manifold. The manifold is a curved Riemannian space including torsion, while the tangent space is a four-dimensional Euclidean space. There is a coordinate transformation between the two, denoted by Q, which is called the tetrad. Curvature and torsion are denoted by R and T. The relationship between the two is d times T equals R times Q. This is called the Bianchi identity, named after the Italian mathematician Luigi Bianchi. The wedge symbol is a special multiplication operator that takes into account the symmetry properties of T and R, and D is a symbol for the derivative. We'll remember this formula because it will appear more often later. If, as in Einstein's general theory of relativity, one sets the torsion to 0, it must hold that R times Q equals 0. This means a strong restriction on the possible curvatures that come out as a solution to Einstein's field equation. Except for very simple cases, this condition is not fulfilled for any solution of Einstein's field equation. In other words, these solutions inevitably lead to a torsion, which, however, is set to 0 by Einstein by definition. This is an irresolvable contradiction that unfortunately falsifies the entire general theory of relativity. Einstein's field equation can only be derived from the Cartan geometry in certain cases of approximation.
We now come to the physics resulting from the interpretation of the Cartan geometry. Because geometry is purely mathematical, we need to determine which physically measurable quantities are associated with each quantity of geometry. This leads us to the axioms of ECE theory. These are generally, first, the tetrad Q corresponds to the physical potential fields. Second, the torsion T corresponds to the physical force fields. Let's start with the electromagnetic case. Then the potentials are the electric scalar potential and the magnetic vector potential, and the torsion corresponds to the electric and magnetic fields. Now, a physical theory requires that one has an equation of state from which one can calculate the potentials and force fields for given physical situations. In electrodynamics, these are Maxwell's equations. If we denote the electromagnetic fields collectively by F and the potentials by A, the Bianchi identity yields D times F equals R times A equals J. Writing this equation in vector form yields exactly Maxwell's equations, with the current J on the right-hand side, which depends on the curvature of space. In other words, the curvature of space is a source of electromagnetic fields. This information goes beyond Maxwell, since in Maxwell's theory the currents are external quantities that are specified. Another special feature in ECE theory, apart from the electric currents and charges, are those of a magnetic nature, named magnetic monopoles. Whether these actually occur in nature is controversial. However, there are experimental indications that this could actually be the case at the microscopic level. An important finding is that there are actually no independent currents, but only fields that are localized in such a way that they are macroscopically perceived as currents. Another important finding concerns electromagnetic waves. In standard physics, they are considered to be transverse waves. These are waves that oscillate perpendicularly to their direction of propagation. However, solutions to Maxwell's equations that represent longitudinal waves are also possible. One also speaks of Beltrami fields, which are named after the Italian mathematician Eugenio Beltrami and are known in fluid mechanics. Here the fields oscillate in the direction of propagation, as is the case with sound waves. This opens up completely new application possibilities. These longitudinal waves cannot be shielded. Some authors also speak of scalar waves in this context, but this is not a correct term.
We now come to the mechanical sector of ECE theory, namely the laws of dynamics and the ECE theory of gravitation. By dynamics we understand the development of a system over time. According to Newton, it follows from the law, force equals mass times acceleration. We first clarify that acceleration is a force field that can arise from either an inertial force or a gravitational force. We know inertial forces from driving a car. Gravitational mass attraction exists, for example, between the Earth and the Sun. Both types of force are equivalent, which has been called the principle of equivalence since Einstein. Incidentally, this principle can be derived from ECE theory. We now proceed analogously to electrodynamics and change the ECE axioms in such a way that mechanical fields now occur instead of electromagnetic ones. First, the tetrad Q corresponds to the mechanical potential fields Q. Second, the torsion T corresponds to the mechanical acceleration fields G. This time, the Bianchi identity gives us the equations of motion of the dynamics. The gravitational field formally corresponds to the electric field. In the electrical case one speaks of Coulomb's law, in the mechanical case of gravitational law. However, this is only one of four laws that come out as field equations of dynamics in ECE theory. A hitherto almost unknown second mechanical force field results, which corresponds to the magnetic field. We call it the gravitomagnetic field. It occurs on an equal footing with the usual acceleration. It acts like a magnetic field, that means, it is generated by moving masses, instead of charges. Since the gravitational force is much weaker than the electromagnetic one cannot perceive the gravitomagnetic field in everyday life. It only appears in satellite movements and in cosmic dimensions. The rotation of the Earth creates a gravitomagnetic field. It has a structure similar to the Earth's magnetic field. The gravitomagnetic field causes the axis of rotation of satellites to wobble, which is called precession. This effect is observed experimentally. Unlike Einstein, ECE theory does not rely on the direct calculation of curvatures, and the torsion is identical to the gravitational field. Therefore, one can use the methods of classical mechanics, which were extended earlier by the special theory of relativity and are called relativistic mechanics. In principle, these are the well-known methods of the mathematicians Leonhard Euler and Joseph-Louis Lagrange from the 18th century. They developed the methods of classical mechanics, which remained valid for about 250 years. The relativistic extension of mechanics has so far hardly been used for gravitational problems. It was assumed that the special theory of relativity on which it is based is not sufficient here. In the light of ECE theory, however, things look different. Since the gravitational field, as just explained, is a torsion field, effects of general relativity, via Cartan geometry, are already present in relativistic mechanics. What Einstein was able to do with difficulty follows from ECE theory in quite simple steps, even if you need a computer for the evaluation. Proof of the correctness of Einstein's theory is that he was able to calculate the rotation of the orbital ellipse of the planet Mercury, which is not possible using classical mechanics. This effect of the rotation of the orbit is also obtained from ECE theory, but with significantly less computational effort. The situation is similar with the deflection of light by the Sun. Since ECE theory introduces the properties of general relativity into classical mechanics, one can apply an extension of the methods of Euler and Lagrange to both problems. So you don't need Einstein's complicated equations. This was previously considered impossible. Also, Einstein's solutions are only approximations for small deviations from classical mechanics, while the ECE solution is general. This makes it possible to calculate arbitrarily large rotations of orbital ellipses, as well as arbitrarily strong deflections of light by celestial bodies.
Flows of gases and liquids are a separate area of physics and technology. They are represented by flow fields that describe the velocity distribution in a flow. This is a specialty of mechanics. One can show that the equations of fluid mechanics are equivalent to electrodynamics. Thus they go back to the same Cartan geometry as electrodynamics and mechanics, and we have a threefold unification of the forces of nature. We can also apply fluid mechanics in the microscopic area. We then come to the structure of space itself. ECE theory allows a clear interpretation of spacetime with torsion and curvature. We call spacetime the combination of time and space coordinates. The crucial point of the graphic interpretation of this four-dimensional coordinate space is to imagine it as being filled with flow fields. Then we can reintroduce the old image of space ether filling all space. The vector potential corresponds to the flow velocity and the scalar potential to the ether pressure. Such an ether is subject to the laws of fluid mechanics, as we know them from air or water flows. So this ether movement can be described by Cartan geometry. Acceleration of ether then corresponds to torsion. So behavior of ether is described in the same way as in electrodynamics and dynamics of mechanical systems. So we have also included the ether through the threefold unification of the laws of nature. In contrast to previous ether models, the ECE ether is subject to the laws of general relativity and is thus described by objective laws that do not depend on an observer's point of view. This ether model has far-reaching consequences for our conception of the universe. We know that galaxies move against each other in space. We can consider this movement as a swimming in the background ether, like wood swimming with a water current. A previously unsolved question has been why stars on the outer arms of a spiral galaxy move at a uniform speed. Galaxies have a core that consists of a large number of stars and accordingly generates a strong gravitation. If this gravity reached to the galaxy arms, the stars would be pulled from there to the center. This is the result of both Newton's mechanics and Einstein's general theory of relativity. However, this movement does not occur. Therefore, additional, invisible matter at the edges of the galaxies, dark matter, has been postulated, which exactly compensates for this effect. However, this type of matter could not be detected by any known scientific method. In contrast, we can explain the shape of the spiral galaxies quite simply using the ECE fluid mechanics. Spiral galaxies are formed by a rotating flow field of the spacetime ether rotating along with the galaxy core. The stars swim in this current, as it were. Angular momentum is conserved in the flow field. This results in a speed of the stars in the direction of rotation that is independent of the radius. So no dark matter is necessary for the explanation. The light from stars is redshifted the further away they are from us. From this one concludes that the universe is constantly expanding. Alternatively, the redshift can be explained quite easily with an optical model. Since the ether is a medium in which light propagates, light will lose some of its energy on its journey over many light years and transfer it to the ether. This is a well-known process in optical media whose index of refraction is slightly different from one. Such an idea is not new, it has been known for years under the name, the theory of tired light, but it has not yet been able to gain acceptance in science, although the counterarguments can all be refuted. Thus, the expansion of the universe can at least be called into question.
Let's now move on to the area of the microcosm, which is also referred to as the quantum area. The name comes from the fact that certain physical quantities, such as the energy levels in atoms, can only have discrete values. That means, they are quantized. The original quantum mechanics does not contain aspects of the theory of relativity. However, one can make quantum mechanics compatible with the special theory of relativity. However, until now it has not been possible to combine the principles of Einstein's general theory of relativity with those of quantum mechanics. There have been many theoretical approaches in this direction, but they were unsuccessful and, moreover, so complicated that they can hardly be understood even by experts. In contrast, ECE theory takes a fairly simple approach. In quantum mechanics, the square of the absolute value of the wave function reflects the probability of a particle being present. ECE theory now identifies, on a microscopic level, the basic function of geometry, the tetrad, with the wave function. This leads to an equation for the wave function that includes quantum mechanical quantities. This wave equation contains the curvature of space and thus includes general relativity. This goes beyond the current state of science. Since the wave equation is derived from macroscopic ECE physics, we have a clear correspondence between the micro and macro cosmos. There are three basic description models of quantum mechanics, which originate from Schrödinger, Dirac, and Evans. The three models differ in the use of spacetime curvature, first without curvature, second constant and third variable. Accordingly, we speak of non-relativistic, special relativistic or general relativistic quantum mechanics. The Schrödinger and Dirac models can be derived from the Evans model. This model is based on the previously mentioned ECE wave equation. It includes spacetime curvature and torsion effects and describes the long-sought union of quantum mechanics with general relativity. Another important result is that statistics in the quantum domain is deterministic. Quantum mechanics calculates with probabilities, so that the same experiments can definitely produce different results. This is due to the wave nature of matter in the quantum domain. A particle that flies through a small hole does not always end up in exactly the same place on the screen. Heisenberg's uncertainty principle states that certain combinations of physical quantities cannot be recorded with any degree of accuracy. However, the general validity of this principle was refuted by Myron Evans and Horst Eckhardt. In principle, quantum physics behaves like classical statistics. One cannot say that processes in nature are subject exclusively to chance. ECE theory enables applications in the quantum domain based on resonance effects. If a wave from the vacuum structure of spacetime hits a hydrogen atom, a resonance effect can occur at a suitable wavelength. This shifts the energy levels of the atom in such a way that a bound electron can easily be detached. This is a possible mechanism for harvesting energy from the vacuum.
In the general theory of relativity, the metric is a central concept. It describes how scales distort when the curvature of space changes. This distortion factor is location-dependent and is denoted by a function m. Spherical symmetries are often used to describe atomic nuclei up to entire universes. Due to these symmetries, it is sufficient that the function m depends only on the radius coordinate. When m takes the value 0, the metric diverges. This corresponds to an event horizon as claimed for black holes. But black holes are a purely theoretical concept of Einstein's theory, which is flawed, as we stated at the beginning. These objects are located behind an assumed event horizon and are therefore not directly perceptible. To that extent they are hypothetical. In ECE theory, the m function corresponds to an ether density and is therefore a general function that is not restricted to Einstein's application cases.
With the help of M theory, we can also describe the world on a small scale. We can build M theory into quantum mechanics. Since quantum orbits have a rotational structure, it is not unreasonable to assume that elementary particles represent local vortices of ether. Inside a tornado, in its eye, it's quiet. Therefore we can assume that the ether density approaches 0 there. This would suggest that there is an event horizon in every elementary particle.
The m function results in an attractive force that occurs in addition to electromagnetism and gravity. We call it the vacuum force. It has no classical counterpart and can only be described using ECE theory. In the electrical case, this force could be crucial in overcoming the repulsive forces between atomic nuclei, which are always positively charged. This could then be an explanation for the low-energy nuclear reaction, LENR, the mechanism of cold nuclear fusion. This represents a new energy source. We have already mentioned that ECE theory has succeeded in unifying quantum mechanics with general relativity. This can also be realized using M theory. The M theory describes the influences of the vacuum, that is spacetime, on matter. This results in corrections in the wave functions, and physical processes that were previously difficult to understand can now be made more comprehensible. In this way, the interactions of atoms with the vacuum can be easily explained. This results, for example, in an additional splitting of the spectra of hydrogen, which is known as Lamb shift. Another consequence of the M function is that movements faster than the speed of light are possible. According to the special theory of relativity, that would be impossible.
Wir haben jetzt sehr viel über Physik gehört und es war mein Ziel, Ihnen die Neuerungen näher zu bringen, die sich aus der ECE-Theorie ergeben. Diese Änderungen sind so massiv, dass sie einen Paradigmenwechsel bewirken. Die letzten Paradigmenwechsel dieser Tragweite waren die Einführung der Relativitätstheorie und der Quantenmechanik. Beides liegt schon 100 Jahre zurück. Einstein hat gesagt, Probleme kann man niemals mit derselben Denkweise lösen, durch die sie entstanden sind. Das trifft auch auf die Probleme der heutigen Zeit zu. Wir haben heute beispielsweise ein Energieproblem und werden es nicht mit herkömmlichen Techniken lösen können. Es braucht neue Ansätze in der Grundlagenforschung, um daraus Methoden abzuleiten, die wir sinnvoll anwenden können. Hierzu ist die ECE-Theorie geeignet. Myron Evans und ich haben diese Theorie in über 15-jähriger Arbeit entwickelt. Sie enthält so viele neue Ansätze, dass es sich lohnt, sich mit ihr zu beschäftigen. Ich wünsche Ihnen viel Erfolg dabei.